In this video, we're going to perform the inverse kinematic analysis for a 2R serial manipulator. So let me draw again the 2R planar manipulator. So here's the XY plane. There's joint 1, there's joint 2, and so there's the end effector. So we call this angle theta 1, and this angle between the links theta 2. It's link A12, this is link A23. And this is just review, or this figure is just review from previous videos. So we're going to solve the inverse kinematics problem. That means that we are given x, y, A12 and A23. So we're given the position of the end effector and we're giving the link lengths. That's the parameters for the robot. And we want to find theta 1 and theta 2. And remember, there are two configurations that can solve this problem. So here we have the elbow down configuration. And I'm trying to draw the elbow up configuration. So this would be the elbow up configuration. So you see there are two separate configurations that can both get the end effector at the same point. Okay. We will step through the solution given here. So we start off finding the angle theta 2. We'll find theta 2A and theta 2B. So here's theta 2A and theta 2B. We're going to do a numerical example here, and so we're going to use this for our data. So we'll say that x is 2.366, y is negative 3.944, A12 is 3, A23 is 1.75. So here again is our XY plane, and the end effector is going to be at about 2.33 and negative 3.944, so right about there. We'll call that point P. So we need to find the joint angles given these two link lengths. And we'll start off by finding theta 2 A and B for the elbow up and elbow down configurations. So we use this equation that comes from equation 2.1, which was the forward kinematics equation. And we know what D and F, what values those take. So these are based on X, Y, A12, and A23. So for this example, it works out that D is equal to 10.5. So 2 times A12 times A23 is 10.5. And F is equal to 9.093. So x squared plus y squared minus this minus that is 9.093. So we find theta 2A is equal to the inverse cosine of F over D. Theta 2 is inverse cosine of F over D. And there are two angles that will satisfy this equation. And we'll refer to those as theta 2A and theta 2B. The inverse cosine is going to give us what we'll call theta 2A. So for this example, it ends up being 30 degrees. And the other angle that satisfies this equation is just the negative of the first one. So theta 2b is negative theta 2a, which is negative 30 degrees. So we've gotten half of the solution. And now we need to move on and get theta 1, the values for theta 1. To do that, or to find those values, we'll use these two simultaneous trigonometric equations. And that gives us, and so these are two equations in the unknown theta 1. Here we have cosine of theta 1, sine theta 1, cosine theta 1, and sine theta 1. And everything in here is known. A1, 2, A2, 3, and cosine of theta 2 is known. The one thing to remember is that theta 2 has two values. So we'll have one scenario where we use theta 2a, and then another scenario where we use theta 2b. And this equation takes the form shown here, and then this is how we will solve for an equation of this form. So for this example, we get that A is 4.516. I don't know what's wrong with this pen, but I'll get it sorted out sometime. E is just X and F is just Y, and so we have two cases for B. B, when we're using theta 2a, we'll call it BA, is equal to 0.875, and B, when we're using theta 2b, we'll call it BB, is negative 0.875. And the reason that there is a there are two values for B and only one for A is that A uses cosine of theta 2, and cosine of theta 2a is the same as cosine of theta 2b. So this value here doesn't change depending on which theta 2 we use. But this one, sine of theta 2a, is the negative of sine of theta 2b. So this coefficient changes here, and that's capital B. This one is B. Okay, so going back to this, so now we have A, E, B, F, and A squared and B squared, and we can use these two equations to get theta 1. So what we'll do is we use the first scenario, that's theta 2a, gives us BA. So we use that in this equation and this equation to get what we'll call, so for that case we're using, oops, didn't notice it was green. Okay, so if we're using BA, then we're going to get a value for theta 1 from the inverse cosine function. So inverse cosine of this stuff will give us theta 1, and we'll call it like that, and that's 70 degrees is what the inverse cosine will give us. And then the inverse sine function is going to give us negative 70 degrees. So using this value of B and using A and E and F, with these two equations, we get the following values. Inverse cosine is going to give us 70 degrees, and inverse sine is going to give us minus 70 degrees. So then we'll refer back to what we looked at a couple videos ago. We're in this situation. So inverse cosine has given us 70 degrees, which is in the first quadrant, and inverse sine has given us minus 70 degrees, which is in the fourth quadrant. So for a case where inverse cosine is in the first and inverse sine is in the fourth, then we know that the actual angle is in the fourth quadrant. So What that means is theta 1a, that is the theta 1 that corresponds to theta 2a, is this, minus 70 degrees. Because it's the value given to you by the inverse sine. Okay, so now we have 3 out of the 4 angles that we need, and we're going to look at scenario B where we have theta 2b. So in this case, the inverse cosine function gives us a value of 48.07 for theta 1, and inverse sine gives us negative 48.07. And this is the same situation as before, where inverse cosine gives us something in the first quadrant, inverse sine gives us something in the fourth quadrant. So in that case, we know that our actual value is in the fourth quadrant, and so we should use the inverse sine value. So we get that theta 1b is negative 48.07. Okay. So let me draw that. Well, I'll go back up to our original drawing. Okay, here it is. So here's x, the x-axis, and the y-axis. And here's the point P. So for the first case, we have that theta 1 is, okay, so theta 1a is minus 70, theta 2a is 30. So theta 1a, and this of course is not totally scale, so there's A12, and there's theta 1a, and here is theta 2a. So there's our minus 70 degrees and our plus 30 degrees, and that puts us at about, or that puts us at point P with the end effector. So that's the elbow up, or I'm sorry, elbow down configuration. And then for the other configuration, theta 1b, theta 1b is minus 48, so that's something like that. And then theta 2a is minus 30 degrees. I'm sorry, theta 2b. So there's theta 1b, theta 2b, and then here is, this is theta 1a. So that would be elbow up. So there's the solution for our inverse kinematics problem. We were given the location of point P, and we found theta 1 and theta 2 that would put the end effector at that point. And the way we did it was by first solving for the two values of theta 2 using this information here. And then we used these two equations, which have the form of this here, and we solved for theta 1a using theta 2a right there, and theta 1b using theta 2b in the places where right here. And so that gave us the inverse kinematics solution.